In this section, we're going to be finding volumes of solids using the disk and washer method. Now, another name for the disk or washer method, and these are really the same method, it just depends on whether the object has a hole in it or not. So disk would be no hole, washer would be if it did, would be volumes by slicing is what our textbook calls it. But it's not really common to hear it called this. So if you're Googling some different examples that you want to look up, you'll have the most luck if you look for disk and washer method. So let's go ahead and look at a quick example of what we mean by the disk and washer method. So the disk and washer method, what we do is we take a shape of a graph and we rotate it around a particular axis. So for our example, let's go ahead and take the graph of y equal x squared. Now this is a parabola opening up, and we're only going to be looking at the first quadrant. And so I want to take this and look at only where x is greater than or equal to 0. So again, this is a parabola opening up into the first quadrant. Now what I want to do is I want to take this graph and I only want to consider it, actually let's not just do greater than or equal to 0, let's do 0 to 1. So we only want to look at this 0 to 1. So we're taking this shape, x equals 0 to 1, this highlighted region right here, and I want to rotate this or spin it around the x-axis. So I'm going to take this entire shape and spin it around the x-axis. Now it's kind of hard to visualize what's going to go on here, but I'll show you an animation in a moment. But it's kind of going to look like a trumpet shape, like a bell shape on the end. So this will rotate and will look something like this on the end. And I want to find the volume of the solid that's created. Now the way we'll do this is exactly the same way that we found area under a curve. We will take rectangles and we'll rotate each of the individual rectangles. And of course we know the deal, as these rectangles get more and more narrow, the incremental width of the rectangle, there's less and less error, and as there's less and less error, I get more and more accurate answers. So I'm going to take each of these and I'm going to rotate it. So I'll rotate this above and below, and then you can see that this is the shape we'll get. Now if we were rotating this about the y-axis, we would get a different shape. So the axis of rotation is important to know what that looks like. So this is the shape that we're going to be getting. Now if you notice, this graph, this solid area that I have here, is touching the axis of rotation. So this area right here is touching my axis of rotation. Now I could choose different axes of rotation, but for now I'll just use this particular region. And there's a little bit in here too, but I don't want to go too far over, but you can see this shaded area. Now when we talk about this, because I'm touching the axis of rotation, this is when I use the disk or the washer method. Now because there's no gap between the graph of the shaded region and the axis of rotation, this is called the disk method. So the general formula for the volume using this disk method is going to be basically following after pi r squared. Because if you think of each of these disks, it's basically just looking at the area of a circle with an incremental width of dx. So it's pi r squared. If I look at the radius, it would be the distance from the top of the rectangle to the axis of rotation. So this would be pi and then r squared, but we'll talk about that in a moment. This would be from A to B in general, meaning where do I start, where do I stop. And then I'm going to look at my radius, and this is going to be cap r squared minus lowercase r squared. In our case that we have written right here, this would be dx. This is the width of the rectangle. So this is going to be the area of the rectangle. This is the width of the rectangle, producing the volume of that disk, that solid that's there. Now this would also work for dy's as well. Now this situation that we're looking at right here is in terms of dx, because if you look at the width of each rectangle, it's on the x-axis. But I could also rotate this a different way, and I could have dy's involved. So the first thing we need to look at is which axes of rotation that we have. So a quick curve sketch is always helpful. Now what's the difference between the cap r and the lowercase r? The cap r is the outer radius. It's the distance from the top of the rectangle to the axis of rotation, and the lowercase r is my inner radius. Now for the disk method, the inner radius is 0, meaning I'm touching. The inner radius is going to equal a particular value if there's a hole in this shape, and it would be equal to whatever the distance was between the bottom part of the graph and the axis of rotation. But we don't have an example like that quite yet. So these are the kind of the setup that we're going to be using. Now for our particular problem that we're looking at, our volume is going to be pi, and we're going to integrate from 0 to 1. Now I know I'm going from 0 to 1 because that information was given up here. My outer radius is x squared squared, and then my inner radius is 0 squared in this particular case because I'm touching the axis of rotation, and the incremental width of each rectangle is dx. So a quick note here, when we're talking about the method that we're using, we'll learn the shell method in the next unit, or in the next homework, but for this particular unit, we're looking at the disk and washer method. So this is useful when your boundary equations, and x squared is our boundary equation here, are in terms of the axis of rotation. So why would we choose to use this method over any other? Well, this is the only method we know so far, but also keep in mind this is what we would use when the boundary equations, and again our boundary equation in this particular case is x squared, basically is in terms of the axis of rotation. Now notice also with the disk or the washer method, my axis of rotation I have marked here, and then when you're doing your handwritten homework you should always mark your axis of rotation just to clarify with your graph. Notice I'm perpendicular to the axis of rotation. So that's another feature that you'll want to keep in mind when we're using the disk or washer method. We're perpendicular to the axis of rotation. So for the disk washer, our rectangles that we draw are perpendicular to the axis of rotation. Okay, and then you can see pretty clearly here that all of these are perpendicular to that axis of rotation. Now we're going to spend most of our time setting these up, not so much time integrating these, because we already have our integration skills in place, but let's go ahead and integrate this first one. If we look at the integral from 0 to 1, my outer radius was x squared squared, which would be x to the 4th minus 0 dx. So we're dragging along that pi. Now we're always doing these in exact form, meaning we don't estimate pi with 3.14. We leave it as pi. So this would be x to the 5th over 5 when I integrate it, evaluated from 0 to 1. I'll pull my constants out front, and I'll have 1 to the 5th minus 0 to the 5th. And that's 1 to the 5th is 1. So my volume here is pi over 5. And because it's volume, this is units cubed. Okay, so units are not squared, they're units cubed because this is a three-dimensional drawing. So let's see what this looks like in terms of not just an xy plane, but an xyz plane. So you can see this is our basic shape. This is our parabola from 0 to 1. And this is that same parabola. This little bit up here is a start of a rotation, but we'll see what's going on here in a second. And what we're going to do, this parabola again, this is the origin point. I have to have this region shown below here because as it rotates I'm going to see what happens here. And you can see as I start to rotate this curve, it starts to create that trumpet shape. So this is going down beneath the x-axis and up over the top into the 4th quadrant. It's even hard to talk about quadrants here because this is a three-dimensional graph, but you kind of get the idea of the shape that it creates then. And so that's the same shape that we created when we took the curve y equal x squared and rotated it about the x-axis. So that's a nice little visual. This is unrotating it, and then this is re-rotating it. So you can see that it's going underneath and around the top, and that's the shape that's created. Now each of these little rectangles is basically one of the rectangles that we drew that it's rotated around. So we can take this two-dimensional xy plane, and with rotation then we can talk about volume instead of just area. So it's a really powerful tool to be able to use to find volume. Now on this particular graph there was no hole or gap between the graph in the axis of rotation, but sometimes we're going to run into that, and when we do, it's going to be called the washer method. But the things to remember are here are with the disk and washer method, the rectangles are always perpendicular to the axis of rotation, and this is the easiest one to use when the boundary equations are in terms of the axis of rotation. And what that means, my equation is x squared, my axis is x, so they're both in terms of x. That doesn't mean I can't do something else, but it means it makes it a little bit easier if we choose that particular method. Let's go ahead and set up quite a few other examples, and remember, your curve sketch is one of the most important things that we can have here to help us figure out what our axes of rotation and rectangles are. For our next example, let's stick with that y equal x squared, but we're going to bound it with another curve as well. So for this example, let's look at taking the curve y equal, let's do something like 11x, which we know is a linear equation, and y equal x squared, which is that nice parabola that opens up. And let's revolve this around the x-axis. So the first thing we need is a quick curve sketch, and then we'll probably need to know our points of intersection of the curves as well. So let's go ahead and get started with a curve sketch. Now if we talk about y equal 11x, this is a line. So just looking up here, this is y equal x squared. This is y equal 11x. It goes through the origin and has a particular slope. You can see that where it does intersect is going to be somewhere up here in the first quadrant. So this is really the only region that I really want to worry about right here. So when I do my curve sketch, I'm going to focus on that first quadrant. Now I'm going to rotate this about the x-axis, and we'll plug that in here in a moment. So the first things I need to do is to find my points of intersection. The way we find our points of intersection is we set our equations equal to each other. So I have 11x equal x squared. Subtract 11x from both sides. We can factor out an x. Use a zero factor property, and I get x equals 0 and x equal 11 for my solutions. So these intersect at x equals 0. And if I plug 0 into this equation, I get 0 back out, same as here. And if I plug 11 in, 11 times 11 is 121, 11 squared is 121, so I'm going to call this 121 up here, and I'll call this 11 over here. So these two graphs intersect at these 2 points. Now you can see from my curve that the parabola is underneath, and the line is on top, it's above. So this is the region that I'm going to rotate. This is a bound region. Now notice this is not touching my axis of rotation, which is the x-axis. I'll plug that in here in a moment. So this is definitely going to be the washer method because I'm not touching my axis of rotation. So my axis of rotation again is the x-axis. So I'm going to note this by the rotation symbol. So I have my points of intersection. I'm not touching my axis of rotation, so this is the washer method. And I'm going to go ahead and sketch in a quick rectangle. Now notice everything is in terms of x, so it looks like to me that the disk washer method would be best, and it has to be best for now because we don't know any other method. So this rectangle, and you don't have to sketch them all in, but you should always sketch in one to set things up. Notice this incremental width is dx, and that's going to be important because this is telling me that everything needs to be in terms of x. So to set this up, I use that idea of area, pi. These rectangles are going to go from 0 to 11, and then I look at my outer radius minus my inner radius. The outer radius is the top of the rectangle, and that's the line 11x. So that's going to be my outer radius squared. And then I subtract out my inner radius. Now I do have an inner radius on this one. The one above we didn't. The inner radius is this curve x squared. And my incremental width is dx. Now technically we have parentheses or brackets around both of these because it's the radius, all of this times dx, but you kind of get that general idea. So this is our correct setup. I'll leave the integration to you. And if you do choose to integrate this, I think you get some pretty crazy numbers. I think you get 322,102 pi over 5. Now on a test or a quiz, depending on how we have these set up, and definitely on your handwritten homework, you should be able to integrate this, and the evaluation, I guess I wouldn't worry so much about, but you should be able to set this up and integrate it at the very least and evaluate it with reasonable numbers, but I wouldn't expect hundreds of thousands in your values here. Okay, so homework, you may or may not need to have the exact form. You need to read the instructions carefully in My Math Lab as well as your quiz. But on handwritten homework and on your test, you always leave everything in exact form unless it asks you to round otherwise. But you usually won't have a calculator, so exact form is preferable. So again, this is an example of taking this graph and revolving it around the x-axis. Now we could also do the same graph. Let's do y equal 11x and y equal x squared, and rotate about the x-axis. Oh, let's do the y-axis. We just did the x-axis. Let's rotate this around the y-axis. So in order to do that, I'm still going to have my same shape. So I know I have that curve underneath. And then I know I have the line that's above. I already know my points of intersection from my work up above. There's 0 and 11 and 121. Now I'm taking this as my shape again, so it's the exact same shape I have above. But I'm taking this and I'm rotating it about the y-axis this time. Now again, we only have one method that we know about so far, so I have to use the disc or the washer. Those are my only options. So I have to be perpendicular to the axis of rotation, so I need to switch my rectangles. So again, I'm going to use the disc washer method. So I need to be perpendicular to the axis of rotation. Now I have a little bit of a problem here. My axis of rotation is the y-axis, but notice my incremental width here is dy, so everything has to be in terms of y, and right now everything is in terms of x. So when we look at this, I need to solve x. X equals what? It equals y over 11. X equal what? X is equal to plus or minus the square root of y. Now if you think about looking at x equal plus or minus the square root of y, we know that we can only choose one of those because we only have half of a parabola. So you can see that all of our x values that we have here in this first quadrant are positive, so I would only focus on the positive here, the positive y values. Now there is another, there's the negative, but if we were in this particular quadrant over here, then I would worry about those. Now it's going to rotate through to that quadrant, but it only starts in the first quadrant. So when I set my equation up, everything has to be in terms of y now. We'll learn some other methods as well, but for now these are our options. Now if you notice on our y-axis, the dy's, the rectangles will go from 0 to 121. Okay, so again, my dy's, I have to think in terms of y's now. And I need to think about my outer radius minus my inner radius. Now in this case, the outer radius is the curve x squared, but now instead of x squared, I have to have it in terms of y. So this is going to look like root y quantity squared for my outer radius. And then my inner radius would be y over 11 quantity squared, and then dy. So you have to be really careful how you're setting these up. You have to think about these pretty carefully. So again, the cap r is my outer radius, so this is root y, and then my inner radius is this y over 11. It's the inside here. Now really what ends up happening is because I have this outer radius, this is this entire distance, and the reason I subtract off the inner radius is I need to subtract off this gap in here. So again, I have my washer method for this particular example. Now when you rotate this one, it'll look like a nice big bowl because it'll rotate about the y-axis. Now for this one, you should be able to integrate it. Evaluating it from 0 to 121, I wouldn't expect that you would do that on a handwritten homework or a test with such huge numbers. I guess a handwritten homework you'll have access to a calculator, but either way you should make sure that you always check your answers, especially on a handwritten homework, because you have access to a calculator or many online resources. But on a test you would probably be using some more reasonable numbers to come up with these. You should always leave this in exact form, which means in terms of pi. Now if you go through and actually integrate and evaluate this into exact form, and exact form meaning in terms of pi, this ends up being 14,641 pi over 6. So if you want to double check that, you can. One thing I'd like you to note is these are different answers. So notice up here my volume, because these are volume, so these are units cubed, was much larger. Now one of the reasons why we can expect this is this figure, this shape, the bulk of this rotating about the x-axis is different than the shape that's created when I rotate this about the y-axis. So I wouldn't expect the same shape rotated around different areas to have the same volume. So that's why we get different answers here. So that's the idea of the disk and the washer method. If you're touching your axis of rotation, it's the disk. If you're not touching the axis of rotation, it's the washer. But it's the same general formula. Part of it just collapses to 0. Now some of these can get a little tricky when we're rotating at about a line that's not an axis. So let's look at a shape, and we'll rotate this about the axis, the x-axis, to get started. But let's go ahead and just look at some of the different shapes that we could get. Let's take y equal 4x, which is a line. Let's also do y equals 0. And let's also look at x equal 2. And we want to rotate this about the y, let's do x-axis. Now the best thing you can do here is a good curve sketch. And then I can look for my points of intersection. So if I get started, I'm going to be rotating this about the x-axis. So I can put in my axis of rotation. So right away I know that my rectangles are going to be dx's because I want to be perpendicular to that axis of rotation. Y equals 0 is this line right here. So this is the line y equals 0. So I'm bounding my graph by y equals 0. X equal 2 we're going to say is right here. Whoops, that's not really a straight line. So x equal 2 is this nice vertical line. And the graph y equal 4x. Well, the graph y equal 4x has the ordered pair 0, 0 at the origin. And then if I plug in x equal 2, it crosses up here at 8. So that's my point of intersection. So this is the graph y equal 4x. Now your points of intersection are easy to find on this one. I take my equations, and for this one I can just plug in x equal 2. So I have y equal 4x, y equals 0 if you want to set those equal to each other. And you can see x equals 0 is this point of intersection. Your other one, I'm going to have this value x equal 2, and I will plug that into y equal 4x. And I get y equal 4 times 2 is 8. So this is the region that I want to rotate. And so we'll take this region and rotate it about the x-axis. Now when I rotate this about the x-axis, when you're setting these up, always draw in the rectangle that you're going to be rotating. You don't have to draw them all in. In fact, you can't draw them all in because there's an infinite number of them. But we'll go ahead and draw in one, and that will give us a reminder of what my variables need to be, and in terms of whether I'm looking at dx's or dy's. Okay, so this is the general shape that I'm rotating. So if I were to rotate this shape, basically it's going to be a circle on this end as I rotate it all the way up to a sharp point. So setting this up, I'm touching my axis of rotation. So here's my rectangle, and this is in terms of dx. We would go pi integral from 0 to 2, because my rectangles are going to run from 0 to 2. My outer radius is this top curve. So my outer radius, it's not just the x that's squared, so we don't write this as 4x squared. We write it as 4x quantity squared. And then the inner radius is the distance between the axis of rotation and the bottom of the rectangle, which we can see is a 0 here. And I always like to show these, plug these in so I can see that I have the inner radius accounted for. And the width of this rectangle is dx. Okay, so when we're setting this up, you have to be really careful. You have to draw that rectangle and always name your method that you're using. This will definitely be the disk method. And again, if you want to call it the washer, you can. It's a washer with the middle radius is 0. And I am perpendicular to the axis of rotation. Now the reason it's important that we name this is in the next homework we're going to be parallel to the axis of rotation using a different method. So if you can name your method, draw in your rectangles, and sketch your curve, it really goes a long way to simplifying this process. I'll leave the integration to you. For this one, if you want to double check, we get 128 pi over 3 units cubed, because again this is volume. Now the shape that we're going to get once we rotate this will look something like this. It's going to be this triangular area that you can see right here, and we're going to rotate this about the x-axis. And this is going to go from 0 to 8 all the way out to, let's say, 2 here. So this is the general shape that we'll get when we rotate that. And being able to visualize that shape is important, but even more important is to make the general curve sketch of the equations. Now most of the equations that we're going to be looking at are pretty basic ones, because if we get too complicated and we're looking at too complicated of a curve that we try to rotate, the integration can get pretty ugly. Now you can also do these shapes and rotate them about axes when you're using trig functions as well, and of course I really like those. So let's go ahead and try and set one of these up. Let's look at the graph of y equals 6 cosine, actually let's do cosine of 6x, and also y equals 0, x equals 0 to bound, and let's rotate this about the x-axis. Now most of the graphs that we've been looking at so far have been rotated about the x-axis, but this doesn't always have to be the case. These are just a lot of the examples that you'll come across in your homework. So to get started, let's go ahead and graph. If we graph y equals 0 and x equals 0, so here's y equals 0. Here's x equals 0, so I'm bounding this, it looks like, into the first quadrant. Now cosine of 6x, let's go ahead and plot some points. Let's do x and y. So if we do 0, the cosine of 0 then is what we have here, and the cosine of 0 is going to be equal to 1. So let's say we're up here at 0, 1. So here's a point. And let's go ahead and plug in another one. This 6x right here is not just a standard angle that we're going to be looking at, so we kind of have to be careful about this. I'm going to take the cosine of 6x, and I want to figure out where it crosses right here, so this is where I would set it equal to 0. So let's think about this. The cosine of 6x equals 0. Well, the cosine is equal to 0 at pi over 2, so I want to figure out where 6x is equal to pi over 2, divide both sides by 6, and I get that this crosses at pi over 12. So we'll call this the point down here, pi over 12. So again, the idea here was the cosine of what angle is 0, the cosine of the cosine of pi over 2 is 0, so that must mean 6x is equal to pi over 2, and then we solve from there. So again, that's going through that step by step. Now we want to rotate this about the x-axis, and again, it doesn't always have to rotate about the x-axis. It just seems like a lot of your homework problems are rotating about the x-axis. So this is the region that we want to rotate. And again, it's bound by the x and the y-axis as well. So this is a bound region. Now because I'm rotating this about the x-axis, the only method that I have so far that I can use, I need to have a perpendicular rectangle to the axis of rotation. So when we're setting this up, I can see that my rectangle is here touching the x-axis, so my incremental width is dx. So this is going to be the disk method, and if you want to say washer you can. It just means there's no hole here because I'm touching the axis of rotation, so the washer method kind of devolves into the disk method, but I'll start this with the disk. I'm perpendicular to the axis of rotation. And it's important to be able to name the method that you're using and why you're using it to help set up. So the disk method, if you'll recall, is based on pi r squared. So pi, and this is going to go, our rectangles will go from 0 to pi over 12. And the outer radius is going to be this curve, cosine of 6x. And I'm not just squaring the 6x, I'm squaring everything. And then my inner radius is 0 squared. And of course my incremental width is dx. Now a couple things here. This is what I use to find my points of intersection up here. And you have to be able to solve a trig equation to do that. So that's going to be a very important skill to have, to know your standard angles, to know where your sines and cosines and etc. are. So that's a good thing to have on your note card for the exam if you're not very smooth with your trig. Now this one, when I rotate this, it's going to kind of be like a bell on its side. So it'll come down like this. And so it'll be this type of shape. When I set this up, the pi I always put on the outside, but it doesn't have to be. So if I wanted to, I could set this up with the pi on the inside, and this could be cosine squared of 6x dx. Now there's going to be a little trig identity that you're going to need to integrate this one. Now remember, in previous lectures we've looked at double angle and half angle formulas, and if you'll recall, the cosine squared of x is equal to 1 plus the cosine of 2x, double angle formula, all over 2. Okay, so this is a rewrite. This is a nice little way, because I can't integrate cosine squared 6x directly. I have to have it in another form. Now if you notice, our angle here is not just x, it's 6x. So that would mean that the cosine squared of 6x is equal to 1 plus the cosine of 2 times that, which would be 12x all over 2. So in order to find my volume here, I need to apply that double angle formula. And the reason I'm popping pi in here is when you do your solutions in my math lab, they don't have a spot for you to write pi on the outside. So I just wanted you to see that pi is just a constant on the inside as well. So if I rewrite this, I'm going to have 1 plus the cosine of 12x all over 2 dx. Then I could pull that pi over 2 out front. Okay, and then I'm left with the integral from 0 to pi over 12 of 1/2, actually just 1 dx, because I already pulled the half out front, plus the integral from 0 to pi over 12 cosine of 12x dx. Now the reason I'm splitting this up into two integrals is the first one's really easy to integrate, the other one's going to need a bit of a u sub. So this is going to come down here. I have a pi over 2 out front. The integral of 1 dx is just x, and I'll evaluate that from 0 to pi over 12. Okay, and then I'll have plus pi over 2. Now the integral of the cosine of 12x. This is a u substitution. I'm going to let u equal 12x. du is 12 dx. So I'd multiply by 12 on the inside, compensate with the 1/12 on the outside, and this is basically 1/12 integral of cosine u du. U substitution. The integral of cosine is sine. So this is going to be pi over 2, and then I have the 1/12. The integral of cosine is the sine of u, which was 12x. And this I'll evaluate from 0 to pi over 12. Okay, now the pi over 2 I split up. It needs to go to both integrals because I split this up into two different shapes here. So as we're working through this, I have my pi over 2 in this first one. When I evaluate my upper minus my lower, I'll have pi over 12 minus 0. Now over here I'll have pi over 24 I could pull out, and then we'll do our upper minus my lower. I'll have the sine of 12 times pi over 12, because I'm plugging in my upper, minus the sine of 12 times 0. So here, this one's pretty straightforward. This is pi squared over 24 for my first one. And then for the second one, let's have a look. Pi over 24 This would be the sine of pi minus the sine of 12 times 0 is 0. Now the sine of pi is 0, the sine of 0 is 0, and again you need to know the values from your unit circle. So this entire second term right here goes to 0, and I'm just left with pi squared over 24 cubic units for my volume. So again, you can use your trig functions with these as well. It's important that you know the unit circle, and I would definitely recommend putting these double angle formulas that are showing up and the half angle formula as well that we've used in previous lectures on your note card, because it will come in handy when we're trying to look at some of these integrals. Now we did a problem before where we took the same area and we rotated about two different axes. Let's do a similar problem. So to get started with this one, let's go ahead and look for the region bounded by y equal 8 minus x cubed. And again, if you know the general shapes of these graphs, that's very, very helpful. You don't have to know them, but it's going to make these problems a lot easier. You could plot points to try and come up with a graph. And I want to bound it by the x-axis and the y-axis. And for my first one, I want to rotate this about, let's do the x-axis, because that's the easier one of the two because everything is in terms of x already. So if I look at 8 minus x cubed is this third degree polynomial opening down, so it looks something like this. 8 would be 8 units up. So let's go ahead and see what that looks like. So it's going to come in here at 8, and it's going to curve down as such. Okay, so and then it crosses over here. This is going to be my x-axis. This is my y-axis, of course. And then my axis of rotation is my x-axis. So the region that I'm looking at here, whoops, let's get the right color. The region that I'm looking at here is this piece right here. Now, because I'm rotating it about the x-axis first, you can see that my incremental width is dx. I'm touching my axis of rotation, so this is definitely the disk method. And again, it's important that you be able to name your method. So I'm perpendicular to the axis of rotation. Okay, so to set this up, I need to figure out what this point is. And it looks like to me if I take 8 minus x cubed, it's definitely going to start right here at 0. So let's look at our points of intersection. I'm going to take 8 minus x cubed and set it equal to 0. I get x cubed equals 8. Take the cubic root of both sides and I get x equal to 2. So that would be this point right here. So it's crossing at 0 or touching at 0 to 2. And I shouldn't say it's touching at 0. My axes are going from 0 to 2. It's touching up here at 8. So if I set this up for my volume, have that pi, and again in my math lab you have to put the pi on the inside, but I like to keep it on the outside because it's a constant, but for my math lab purposes you can see that it can go either in or out. This will go from 0 to 2, and your outer radius would be 8 minus x cubed quantity squared. Your inner radius, I'm touching my axis of rotation, so that's equal to dx. Now in order to integrate this, you're going to have to FOIL this out. You cannot take the 2 and distribute this to get 8 squared minus x cubed squared. You have to FOIL it out first, outsides, insides, and last. And it's really important that you remember that because a lot of people like to just go ahead and distribute the squared, but you can't. Now if you go through the process, I'll let you look at the integration. You should get 576 pi over 7. Now this is rotating about the x-axis. Now let's do the same problem and let's do y-axis rotation. So let's use the same picture, but this time let's go ahead and use that y-axis rotation. So it's the same picture, but now I'm going to use dy. So my volume, my rectangles will go from 0 to 8 because I crossed at 8 here. And then instead of the outer in the inner radius, we're still doing that. Think of the right minus the left, the right curve minus the left curve. Now what I have to be careful of here, if I have y equal 8 minus x cubed, I need everything in terms of y. So if we solve here for x cubed, I get 8 minus y, and then I take the cubic root of both sides, I get the cubic root of 8 minus y. So that's one way that we could look at this. Now as we're setting this up, we could also write this in exponential form. So if I wrote this in exponential form, this would be x equal 8 minus y to the 1/3. So my outer radius is this curve that I've had to redefine as 8 minus y quantity to the 1/3 quantity squared. Now this is touching my axis of rotation, so my inner radius is 0 squared, and everything is in terms of dy. Now if you run through your integration here, you'll end up with 96 pi over 5. So if you want to compare these to say which one is larger and smaller, you can clearly see that the 576 pi over 5 is going to be the larger area. So rotating this about the x-axis creates a larger volume, I should say, not area but volume. So this is the larger of the two, and then down here this one is the smaller. And again, if you needed to look at a decimal approximation, you can, but the easiest way to compare these is if you notice the denominators are about the same, they're pretty close, but the numerators, this is way larger than 96, so I can see that this overall fraction is going to be larger. So this is an example of comparing the two volumes that are created by rotating these about different axes of rotation. So these end up being some pretty interesting problems. The best thing you can do is to have a good curve sketch to begin with. Be aware of what your axis of rotation is. Make sure you draw in your rectangles so you have a good visual as to what's your upper and lower curve or your outer and inner radius, and kind of work from there. As we're working through these, if you have questions, as usual, please let me know. If you're stuck on the graphs, you might want to check your graphs on a calculator or in Wolfram Alpha, Mathway. Desmos is my favorite graphing tool. So you can kind of get used to some of these graphs. Of course, on a handwritten homework, you're welcome to use those tools as well, but you need to show your complete work. On a test, you will need to know what these graphs look like. Also, you should be very careful about leaving your answers in exact form. That means in terms of pi, not decimals. You always evaluate your trig functions using the values from the unit circle, not decimals either. If you have any questions, please let me know. I'm happy to help. We could, if you let me know and you need help, we could meet online in office hours, or you can send me a screenshot of your question as well. Good luck.